Hello, welcome to this lesson. In this video, you are going to learn how to solve differential equations of this form. But before you go ahead and do that, I'd like to explain some few things to you to help you understand this whole concept. Okay, so in general, if you have a differential equation of the form m of xy, okay, plus n of xy dy dx equals 0, then we can actually apply this method that I'm about to teach you. So when you have a differential equation of this form, the first thing you have to do is to test for exactness. Okay, and to test for exactness, all you have to do is to find the partial derivative of m of xy with respect to y, and also the partial derivative of n of xy with respect to x, and compare these two and see if they are the same. If they are the same, then the differential equation is exact differential equation, but if they are not, then it is not exact. But in this video, we are only going to talk about exact differential equation. So if the differential equation is exact, we are going to have my is equal to nx. Okay, and it means the differential equation is exact. Okay, so now if the differential equation is exact, then it means that there is a certain function phi of xy, okay, such that the partial derivative of phi of xy with respect to x will give us m of xy, okay, and then the partial derivative of phi of xy with respect to y will give us n of xy. Okay, so for this reason, I can rewrite the general form as phi of x plus phi of y dy dx equals 0. So our main goal here will be to find the function phi of what? Xy, okay, which can find the partial derivative with respect to x to get n of xy, and then with respect to y to get n of what? Xy. So let's look at how you are going to find this function. You are going to do that using this example that I have here. So the question is giving us 2xy minus 9x squared plus 2y plus x squared plus 1 dy dx, and this is equal to 0. So you see that this is of the same form as the general form that I gave. Okay, so you should have a 0 on one side, and also you should have the sign between the two terms to be plus. So the first thing you have to do is to identify our m of xy and n of xy. So the m of xy in this case will be equal to 2xy minus 9x squared, okay, and then the n of xy will be equal to 2y plus x squared plus 1. Okay, so you're going to find the partial derivative of m of xy with respect to y. When you do this, you're going to get my, then this will be equal to the partial derivative of 2xy will give us 2x because the y become 1. And then for minus 9x squared, because you don't have any y variable there, it will become 0. So let's do same for n of xy. That one too is the first term, which is 2y, becomes 0 because it doesn't have any x variable there. And then the second term becomes 2x, and then the one becomes 0 also. So you see that both partial derivatives are equal. So you see that the differential equation is exact. Okay, so since the differential equation is exact, then it means that there is a certain function phi of xy that when we differentiate with respect to x, we are going to get m of xy. And then when we differentiate with respect to y, we are going to get n of xy. So that function is what you want to find now, and then that will be the solution to this differential equation. Let's look at how you are going to find this function. So to find this function, all you have to do is to integrate either m of xy with respect to x, or integrate n of xy with respect to what? Y. So let's look at that. I'm going to choose one, okay, because you have to choose one, depending on the one that will be easy for you. In this case, they are both easy, so I'm going to go with m of xy. So we are going to have the function phi of xy, okay, to be equal to the integral of m of xy with respect to what? X. Okay, this is what you're going to have. Okay, you're going to have this because we are saying that when we differentiate phi of xy with respect to x, you're going to get m of what? Xy, right? Okay, so what that means is that the partial derivative of phi of xy is going to give us m of what? Xy, okay? So when we integrate m of xy with respect to x, we are going to get part of phi of xy, which will be part of the solution that we want. That's why we are doing this. So you go ahead and then integrate m of xy to get part of what? The solution. Do you get it? Then from there, you go ahead and then find the remaining part to get the complete solution. So we are going to have the integral of m of xy with respect to x, which is the integral of 2xy minus 9x squared, okay, dx. So when you do this, you will have to bring in a constant of integration. But since the integral of m of xy with respect to x is giving us only part of phi of xy, you will have to, instead of bringing constant of integration, bring a function of the other variable, which will be y, okay, so that we will be able to find the remaining part of the solution. So let's look at how this is going to be. So we're going to have the integral of 2xy with respect to x to be 2x squared y over 2, and then the integral of minus 9x squared with respect to x to be minus 9x cubed over 3. Then instead of constant of integration, because we are not getting the complete solution, we are going to bring a function of the other variable y, okay, so that we can find the remaining part of the phi of xy function. Okay, so from here we can simplify this, and you are going to get x squared y minus 3x cubed plus h of y. Okay, so when we get here, okay, there are two things that we can do here, okay, to actually find the h of y, because we know some parts of the solution, but we don't know some parts because of the unknown function h of y. So there are two things that we can actually do here. So let's look at what we are going to do. The first thing is to differentiate the phi of xy, okay, with respect to y. Then after that, you do a comparison to n of what? Xy, okay. Then from there, you can integrate what you get after the comparison to find the unknown function h of y. Let's look at that. So I'm going to have the partial derivative of phi of xy, okay, of phi of xy with respect to y, okay. So this will give us 2xy. Sorry, this will give us 2. We are differentiating with respect to y, okay. So the y will become 1, okay. So for that reason, I'm going to have x squared rather, okay. I'm going to have x squared rather, and then minus, for this term we don't have any y there, so it becomes 0. So we are going to have plus the derivative of h of y with respect to y, which will give us h prime of what? Y. Okay, sorry about that. So that gives us h prime of what? Y. Okay, so now what we are going to do is that we are going to actually compare this to n of what xy, right? Because we are saying that anytime you find the partial derivative of phi of xy with respect to y, it should be equal to n of what xy. That's from this point. Okay, so for that reason, we're going to equate this to n of what xy, and then do some comparison there. So let's do this. So I'm going to have s squared plus plus h prime of y, okay, to be equal to n of what xy, and then that's equal to 2y plus s squared plus 1, right? So from here, you can see that s squared is common to both sides. So you can say that h prime of y is equal to 2y plus 1. Okay, but we actually want to find h prime of what? Y, right? So we will have to integrate this. So we are integrating this with respect to y, okay? Because at this point, okay, at this point, the function you will get after the comparison, the function you will get must not contain the variable x. It must contain only y so that you can integrate with respect to y. So after you do the comparison and you get the h prime of y to be equal to a function that contains the other variable x, that should let you know that there's a mistake there, because the function you should get should be a function of what? Only y. Okay, I mean what you got. You see after the comparison you got h prime of y to be equal to 2y plus 1. Okay, before we got the integral symbol. So this is what I mean. I mean this function should be a function of y only. There shouldn't be x in it. That's what I mean. Okay, so let's do the integration. When you do the integration, you're going to get h of y to be equal to, then integrate 2y with respect to y, you're going to get 2y squared over 2. Then when I integrate 1 with respect to y, you're going to get plus y. Then you can bring the constant of integration c now. So then we're going to get h of y to be equal to y squared plus y plus c. So now you can substitute this back into the phi of what xy that we have here. Then you can get our complete solution. So I'm going to have phi of xy, okay, to be equal to x squared y minus 3x cubed plus h of y, which is now y squared plus y plus c. So this now becomes the general solution to this differential equation.